So welcome to this. This is the Further Maths Support Programme online revision session for MEI Statistics 2, and in this session we're going to be looking at the normal distribution. 4 key points that you need to be able to do. One is use the distribution as a model. We've got quite a bit of that. We need to be able to use the normal as an approximation to the Poisson and binomial. Now, based on that, because Poisson and binomial are discrete and the normal distribution is continuous, we will need to be able to understand how to use this thing called a continuity correction. And we need to be able to carry out a hypothesis test for the mean. So, straight into questions with this one. January 2011, question 3. We've got a random variable x, and it represents reaction times in milliseconds of men in a driving simulator, and we're told that x is modelled as a normal distribution with a mean of 355 and a standard deviation of 52. So we're asked to work out the probability that x is less than 325. Now we can't do this directly. We have to actually standardize our data because in the formula booklet we have a cumulative frequency table as long as the mean is 0 and the standard deviation is 1. So we have to standardize. So to do this we use our standardization formula. So z is equal to x minus mu over sigma. And if we calculate that through, that's going to give me a negative value, 0.577. Now your table only deals with positive z's. So this is the probability of z being less than minus 0.577. And by symmetry arguments, this is the same as 1 minus the probability of z being less than 0.577. Okay, so just before we look at the answer, I just want to show you so far we've got two marks. We've got a method mark for standardizing, and we've got another method mark for actually getting the structure correct. So all we're left to do now is look this up in a table. So a z value of 0.577 comes from the table thus. So we look up 0.57, which is 0.7157, and we're going to add to the last two digits 24. 24 if you wish. So that's going to give me a 187. So 0.7181. So then I said that the probability of working out the fact that x is less than 325 is going to be 1 minus this. That's what we wrote earlier. And if we do that, we get 0.2819. Okay, and that will be your final accuracy mark here. So that's quite nice. Now part B follows pretty much the same structure, except you need to realize that this is the probability of x being less than 400 minus the probability that x is less than 300. So we standardize in exactly the same way. So if we look at the first one, z is equal to 400 minus 355 over 52. And if we look at the second one, that's 300 minus 355 over 52. Standardizing each, this one is going to give me a z value of 0.865. This one is going to give me a z value of minus 1.058. So of course, because it's negative, we need to just look at this one carefully. So this one is just probability of z being less than 0.865. This one we're going to have to do 1 minus the probability of z being less than 1.058, so that excuse me, so that we can use the table. So first of all, 0.865 is going to give me a probability of 0.8065. It's awkward, isn't it? And a z value of 1.058 is going to give me a probability of 0.8549. So again, I really want the negative z value. So we take that away from 1 as I discussed a little bit earlier. So that's 0.1451. So your answer to this now is the probability of x being less than 400 minus the probability of x being less than 300. And we've got both of those values now. So 0.8065 minus 0.1451. And that's going to give me 0.6614. If you've used a graphical calculator to do this, then your number will be slightly different because it's slightly more accurate. Okay, so there's 3 marks for this, and it's the same sort of idea. You're going to get 1 mark for standardizing. Effectively, you're going to get another method mark for getting the structure correct, i.e. getting this value out here, and then an accuracy mark at the end. Okay, so this time we're using things backwards. We're trying to find what's called a percentile. And there's some issues with this that we just need to be aware of. So you need to be aware, first of all, that the complement of 0.2 is 0.8. Complement probabilities add up to 1. Secondly, this is a cumulative probability of 0.2. That's going to give you a negative z value when you standardize. And that's really important to bear in mind. Okay, so if this is 0.2 at the bottom, you can see we're going to get a negative z value. Now, the reason I say this is because when you look at your tables, your probabilities, your percentiles are for 50 percentiles and above. So we have to look up what we call the 80th percentile here. So if we look up the 80th percentile, that's going to give me a z value of 0.8416. However, I know that the probability is less than a half, so I know that's definitely going to give me a negative z value before I even start. Okay, so to get to that point, you're going to get a B mark, either for getting 8416 without really worrying about the sign. Then we need to realize that we need to standardize this. So k minus 355 over 52 should equal that z value. And for that, you're going to get another method mark in this case. So if we tidy all of that up, shove things around and solve it, we're going to get 311.2. And of course, that's your final accuracy for this. Okay, so that's quite a nice way of tackling these questions. So then we're going to a hypothesis test. So there are 8 marks here. Okay, so it is thought that women have a different mean reaction time from men. In order to test this, we're going to take a random sample of 25, and we work out that the mean reaction time of those women is 344. So that's your X bar. You may assume that women's reaction times are normally distributed with a standard deviation of 52, and we're going to ask to carry out a hypothesis test to see whether they have a different mean. So the first thing to do is to set your hypotheses and state your parameters. So the mean that we use is going to be 355 because we're seeing if it's different from men. Now if it is different, that leads me to state a two-tailed test. Okay, and we also need to define mu. So mu is reaction rate for women. Okay, so at the minute we get a B mark for each hypothesis and also a B mark for correctly stating what mu is. So that's really quite nice. We get quite a lot of marks for that. So things we need to realize, this is a two-tailed test. Okay, so your significance level is going to be split. If I just draw a picture of this, it's going to be split half and half. So we're going to have 2.5% at the bottom and we're going to have 2.5% at the top. Okay, so in other words, to work out this value here, we're going to be using phi inverse of 0.975, and of course this will just be the negative of that when we get there. Okay, so that's going to allow us to find something called critical values to do this question. Okay, so here we go. We're going to work out the test statistic. Now in this particular case, it's written in your formula booklet, but to test for the mean, this is what your test statistic is, and we have every value we need to work this out. So we've got sample mean 344, we've got our assumed mean to be 355, we've got our sigma to be 52, and our sample size is 25. So if we calculate all of that, we're going to get minus 1.058. So this is called your test statistic, and what I'm interested in really is how big it is. I'm not really worried about its negativity. Okay, so as I've said, to find your critical value, we're looking up this particular value here, which is 1.96 from your tables. Okay, and we can clearly see here that the value of your test statistic is less than the modulus of your critical value. This always leads us to reject H0. Okay, so far we've just picked up another 1, 2, 3, 4 marks. Okay, so we've picked up a method mark for correctly finding the test statistic and an accuracy mark for getting the correct test statistic. We then get a B mark for getting the correct critical value, and we get an M mark for sensible comparison. Your final mark is about getting the conclusion in context correct. So we are, do not reject H0. So we are then having to write our comment on here. So there is insufficient evidence sufficient evidence to suggest that. I'm not going to write the next bit because I'm going to show you how it works. You then go all the way back to the context. So this is what you would then write. Okay, so there is insufficient evidence to suggest that women have a different mean reaction time from men. You literally take that from the question, and that will give you, you need to write it obviously, but that will then give you your final accuracy mark. Okay, so just to clarify, if your test statistic is less than your critical value, that leads you to not rejecting H0. If it was the other way around, then you would reject H0. Okay. So moving on to another question, we've got some Braeburn apples, and we're told that they're normally distributed with a mean of 210.5 and a standard deviation of 15.2. So the first part of this question is very, very similar. I want the probability that they are at least 220 grams. Now that's going the wrong way, so I much prefer to realise that that can be swapped around, and then I'm just dealing with this probability, which of course again needs standardizing. So Z is equal to 220 minus 210.5 over 15.2. So my Z value that corresponds here is going to be 0.625. So what I'm really working out is 1 minus the probability of Z being less than 0.625. So as in previous questions, I've got 2 marks now. Okay, one for standardizing and one for getting the structure correct. So 0.625 again. Just go through this. So 0.7324, and I'm adding 16. So that's 0.7340, and I'm looking for 1 minus that. So that's going to be 0.2660. So again, accuracy mark there. So quite a nice question, these. Then it gets a bit more fun. So apples are sold in packs of 3, and you may assume that the weight of apples in each pack are independent. Find the probability that all 3 apples weigh at least 220 grams. So the key word here is independent. So that's the fact that the first apple weighs at least 220, and the second apple, and the third apple. And because they're independent, we can just multiply all of those together. So you get 1 method mark for getting to that particular point, which is quite nice. As long as you substitute your numbers in. Now, as long as you use your answer from part 1, then everything is fine for this part anyway. Okay, and as long as your answer is then correct based upon that, you're then going to get all of your marks. Okay, so you get a method mark for cubing your answer to part 1, and then an accuracy mark. It's actually a follow-through accuracy mark. So again, if you've made a mistake, then that is followed through, which is quite nice. Okay, so we're then told we have 100 packs, and we want to state the exact distribution of the numbers of 100 packs in which all 3 apples weigh at least 220 grams. So really we need to be redefining here. So let Y be number of packs containing 3 apples weighing at least 220. So here Y is actually now a binomial distribution, because I'm now talking about the number of packs, and there are 100 packs, and the probability that all 3 apples weigh at least 220 grams is this 0.0188 that we had previously. Okay, so you get two marks for that because you're stating the exact distribution. So you get 1 for stating it's binomial, and you get another mark for getting both of your parameters correct. Using a suitable approximating distribution, find the probability that in at most one of these cases, in at least one of these packs, all 3 apples weigh at least 220 grams. So I'm really looking for the probability that Y is at most 1. So Y is less than or equal to 1. That's what we're looking for. Now, you realise quite quickly that we can't really do the binomial with this because it's a bit clunky, and it does ask us to use a distribution. Okay, so those with graphical calculators, you have to use the approximating distribution. So we notice that n is large, p is small, and we also notice that np is actually equal to 1.88, which is less than 5. So as a consequence, we're actually going to model this using the Poisson distribution. So this is going to be a Poisson 1.88. Okay, it should be Y I'm using here, not X. Sorry, there we go. So this is now quite nice. So the probability that y is less than or equal to 1 is going to be the probability of y equaling 0 plus the probability of y equaling 1. So that's going to be e to the minus lambda times by lambda, which is 1.88. Let's get rid of that for a second. So 1.88 to the power of 0 over 0 factorial plus e to the minus 1.88 times by 1.88 to the 1 over 1 factorial. Okay, so before we get the answer, let me show you where all your marks are at the minute. So we're going to get one more mark here for stating it's Poisson. You're going to get 1 mark for stating it's a Poisson with a mean of 1.88. We're then going to get a method mark for either of these two probability formulae correct. You're going to get another method mark for adding them together, and then you get only 1 accuracy mark for actually working it all out. Okay, so if you work all of those out on a calculator, you're going to get 0.1525 plus 0.2869, and then your final accuracy mark here is for adding those together, so 0.4394. And again, there'll be tolerance in the answer for that. Okay, explain why it's suitable. Well, we've gone through that at the beginning. N is large, P is small. So that will get you that final B mark there. Okay, so that's really quite pleasant. And again, we're looking really for the fact that actually NP is less than 10 would also be a sensible reason for this as well. Okay, so supermarket also sells Cox's orange pippin apples, and the weight of these apples measured in grams are normally distributed with a mean of 185 and a standard deviation of sigma. So I'm not told about that yet, but I'm given that 10% weigh less than 170 grams. So the probability that the Cox apples weigh less than 170 grams is equal to 10%. And we've got to calculate the value of sigma. So again, it's very similar to a previous question. This is a probability which is going to lead to a negative z value when we do this. Okay, so we're going to unstandardize it in the same way as we've done before. So if we look up 90%, because that's what exists, we're going to get a z value of 1.282. So therefore the probability that x is less than 170 equals 0.1 leads us to exactly the same statement as the probability that z is less than minus 1.282 is equal to 0.1. Okay, so we now unstandardize. Again, z is equal to x minus mu on sigma. So z minus 1.282 must equal 170 minus the mean, which is 185 in this question, divided by sigma. So sigma is equal to 170 minus 185, all divided by 1.282. Okay, so we've got 2 marks so far. 1 for getting the correct z value, 1 for standardizing the formula correctly, and then of course you get your final mark for just calculating that through. So sigma in this particular case is going to be 11.7. Okay, and it's correct answer only in this particular case. So again, quite a pleasant question as long as you know how to unstandardize. Okay, we're then asked to sketch the distributions. So this is really an exercise in just checking how these work. So I'm just going to show you the answer rather than draw these, and show you the key points. So the Cox's apple had a mean of here, and the Brayburn's had a mean that was much higher, 211.5, wasn't it? So we need that, but also the Brayburn's had a wider standard deviation. Okay, the Cox's had a standard deviation of 11.7. Okay, and the Brayburn's had a standard deviation that was slightly wider than that. Okay, had a standard deviation of 15.2. So what we're looking for here is some indication that the mean here is at 210.5, and some indications here that the mean is at 185. That's quite important. We weren't worried about the scale on this axis, but we are worried about the scale on the x-axis. And you had to demonstrate also that the Brayburn had a wider standard deviation. Again, it's very difficult to draw standard deviation here, but it's definitely wider. That's the key thing. Okay, for here it was 15.2. For here it was 11.7. So it's very important to indicate that width. Okay, so let me just talk to you about where your marks are allocated for this. Okay, so you're going to get graph marks for this, G marks. So you get G mark for getting the shape correct. Okay, you get a G mark for making sure that the means are correct. You get a G mark for the Brayburn height to be lower than the Cox's height, and that's because you've got a wider standard deviation. It flattens the graph. And then for Brayburn's as well, you need to demonstrate that it is a wider graph. Okay, so all of those things. Now the reason it's lower is because it's wider, because the area is fixed to be 1. Okay, so that covers most of the salient points about how to deal with normal distributions. It doesn't cover continuity corrections, so you need to make sure that you're able to do continuity corrections in that context.